science and biology, you've got to go to the Galapagos, and Monteverde is also one. And so when I was invited by Rebecca to come, it works out that we are able to do this. We've just come from a one-week workshop outside of Uvita, near the Oso Peninsula, and are about to head to the other side of the Children's Rainforest for another workshop next week at a place near Fortuna. And so this day fit in perfectly, and I'm really thrilled to be here.
You seem to laugh a bit.
No, that's great. Thank you, Chris, for being my translator. So, what I want to talk about today is a field that has 1 foot in nature. 1 foot in biology, 1 foot in ecology, 1 foot in understanding the natural world. And it has its other foot in our world, in what it means to be humans and how we live on the planet. So I want to talk to you a little bit about that. We call this, and a way to think about it is it's innovation inspired by nature. And I'm going to really unpack this phrase over our time here. I'll probably talk for maybe 30 minutes, 35 minutes or so, and then we got plenty of time to ask questions and go deeper on anything that anybody has any questions about. You all recognize this? It was almost 50 years ago that, or more than 50 years ago, I guess now, where we got up and we got to take this picture and turned around and looked at this incredible blue marble and realized what a precious place this planet is that we're on, right? In the big black sea. And we know, and most of you, I presume, have some scientific background, that Earth has been around for 4.5 billion years. And 4.5 billion actually doesn't sound like that much when we have, I don't know, $12 trillion deficits in the United States, and you've got multi-billionaires and companies that are worth trillions of dollars. So 4.5 billion doesn't sound like a lot, but because it's such a big number, I want to unpack it a little bit for you so we can get anchored in what it means to be here on this blue marble. So if we take 4.5 billion years and we compress it into 1 year, because we can all get our bodies and our minds around how long 1 year is. So the age of the Earth is just a breath past midnight on January 1st. Okay? And today, in 2023, we are just a breath before midnight on December 31st. So I want to talk about what happened in that year. Okay? So the first 6 weeks, 7 weeks, it was the primordial soup, right? It was the volcanoes and, all sorts of activity that was just the planet gelling. And it wasn't until February 25th that life appears on the planet, the first life forms. That's 3.85 billion years ago, give or take, right? As we find and make new estimates. But it's been around since February 25th. We like to think of that as life's birthday. It took a full month of those early single-celled organisms before we had photosynthesis. Okay? It showed up in March 28th. And we know that when photosynthesis arrived, an ability to turn photons from the sun into oxygen, okay? Then we shift the planetary conditions, that all sorts of other things began to cascade. But it wasn't until August 16th that we even had any multicellular organisms. So all the way through April and May and June and July, it was just single-celled organisms in the sea. That was it. So multicellular organisms on August 16th, and it wasn't until September 17th that we actually have sexual reproduction, that we begin to mix genes. When we begin to mix genes, then all sorts of new possibilities can occur. And it wasn't until 6 weeks ago, November 15th, that anything that we can really detect shows up on terra firma, right? So the fungi are literally only 6 weeks old in our year, our compressed year. Fish, meanwhile, in the sea, we start seeing our first vertebrates show up November 20th. Land plants, November 22nd. Insects, November 24th. Amphibians, this month, beginning of this month, the first amphibians, December 2nd. As soon as they figured out how to let that skin dry out, move a little bit away from the water. Reptiles, December 6th. And of course, the reptiles ruled the planet for 350 million years. They only showed up December 6th. And they were quite the success story. Mammals, first mammals, December 13th. Birds, December 18th. You might be shocked to learn that flowers didn't show up until December 20th. The dinosaurs, really bad Christmas night for dinosaurs. So dinosaurs went extinct, 6:30 p.m. That's when the asteroid hit the planet. And of course we know that had a huge impact on the planet, 67 million years ago, and wiped out the dinosaurs. That was 6 days ago. Just 6 days ago. Hopefully by now you're like, we haven't showed up on the scene yet. Where are humans in this big, long year? Well, it turns out that hominids, right, the first two-legged ancestors, not even Homo sapiens, but hominids showed up just 35 minutes ago. Right? 35 minutes ago. Here we are. Right? No, sorry. I don't have my time on. Oh, 12:25. There we go. So 11 hours ago, 11 and a half hours ago is hominids. Thank you. I got my 25 minutes. So we showed up 35 minutes ago. All right? Homo sapiens is 35 minutes old in our year long of the planet. Agriculture, when we started settling down and sort of not being hunter-gatherers, 1 minute. 1 minute ago. And the entire Industrial Revolution, life as we know it, that defines all the things that we do, our cell phones and X, Y, and Z, 2 seconds. 2 seconds in that 4.5 billion years. Are we the pinnacle of evolution, right? Is this what everything since February 28th was leading to? As a biologist, I have to ask and acknowledge that we are the only species that has to build equipment to protect ourselves from ourselves. Is this really where we want to go? That we create this world that is not creating conditions conducive to life? Nope. Definitely don't think so. So at its core, that's the essence of the work that we're doing, is we're saying there's some brilliance in that time, right? And the reality is the planet is ours, but it's not ours alone. We are just one member of minimum 30 million. I'm sure all of you that are working here are like, oh, that's such a low estimate. It's probably closer to 100 million, maybe even more. So what does it mean to find a place to fit in on the planet? Right? What does it mean to be an organism amongst 100 million other organisms living well? I'm going to do a quick check. Is my pace okay for you?
Perfect.
Okay. You can just a little bit more. Sure. Yeah, just a bit. So what I'd like to suggest is that we actually have more in common with these other 100 million species than you might think. And if we start asking and start looking and going, we do share a number of traits. We're not the only ones that have to nurture our young. We're not the only species that needs to send signals. Nor are we the only ones that has to manage moisture or resist dehydration. We aren't the only species that has to figure out how to attach to wet surfaces or dry surfaces, or just even attach. We aren't the only species that has to learn how to pack efficiently, as we put 7 of us in a small van with a lot of luggage, right, today. How do we pack efficiently? We're not the only species that has to build lightweight and strong. This is the inside of a bird bone. Inside. Nor are we the only ones that needs to protect fragile parts or manage toxins. There's other species that have to figure out, how do we change color? How do we even create permanent color? We have to manage resource supply, so do other species have to manage resource supply. We need to distribute resources in a way that's effective across the ecosystem. We're not the only ones that have to build a circular economy or organize without managers, or even just self-organize. These are, people think of them, I call them slime molds, of course, but they're actually social amoeba. They're not a mold, they're an amoeba. And they come together when the resources get scarce. They collectively grow a stalk, so they can get up off the surface just a little bit in order to distribute and get into new places where new resources are available. We're not the only ones that have to foster partnerships. I'm sure you all know about the relationship between why bother climb down out of a tree to defecate if it isn't in the spirit of good partnership. Or even build resilience. This is part of our immune system. As we know from the last few years and this whole planet, what it means to be working on how to be more resilient, whether it's inside our own immune systems or what it means for a society. Nor are we the only ones that has to learn how to leverage patience, right? Patience pays off, or be locally attuned, or even engineer ecosystems and create places and niches and homes for others to live. And just about every question that I have been asked in the 25 years that I've been doing this, I can say there's another organism, there's another living system that has had to solve that same challenge. The one exception was managing 1,000-degree temperatures in a supersonic jet. Even the hydrothermal jet, pumps at the bottom of the sea did not fit that, right? So, can nature help us innovate? I mean, if the bellbird can come up with this, right? Clearly, there's creativity and innovation potential that we can learn from, especially as we come to a point on our planet where what we're doing now is not suiting, right? It's not suiting us. We are on the extinction shortlist as a species. And if we want to continue to thrive and not take down a bunch of other species with us, we need to innovate. We need to come up with better ways of being here. So that world of what most of you know well, probably, this biology, nature, life, and this idea of this separate world over here of design, innovation, and technology don't have to be separate. And that's the work that I and many of my colleagues here are deeply involved in. We're bringing those worlds together and working in this interstitial space between the two of them. And that is the world we call biomimicry. And by definition, when we talk about biomimicry, we refer to it as the conscious emulation of nature's genius. And those 4 words were very carefully chosen. So conscious implies intent. We actually make a choice to go out and learn, not about nature, but to learn from nature. And the emulation is also really important because it's not about copying. We will never build a helicopter laws of physics simply won't allow it. But can we emulate some of those design principles that make it so efficient and effective for a dragonfly to hover and go backwards and forwards, and build those into our flight machines? Right? What are those design patterns? And I'm going to share some examples with you. But that's what we mean by emulation, right? Emulation. And nature's genius is, well, she's been around since February 25th. Right? And our entire way of solving problems, pretty much at most, if we're generous, we can say is 35 minutes old. But for the vast majority of it, we're relying on the last 2 seconds of experience on the planet. And so that idea that, well, there's been a few kinks worked out. The problems have been worked out. And in fact, with the exception of some major extinction events, what we see here on the planet are the success stories. They're the ones that are figured out what it means to live here well now and have the systems in place to serve that going forward. So we look to nature as our model, as a measure, and a mentor. And this work, biomimicry, this field, is an entirely new way of viewing and valuing nature. Not based on what we can take, right? The Industrial Revolution was about take wood, take rocks, take soil, take coal, take oil, take nature, right? For our good and only our good. And it totally changed that and says, can we actually learn from them, right? Help us learn how to be better humans on the planet. And it's important to acknowledge that while this is an emerging discipline, you know, we offer a Master's of Science degree in biomimicry at Arizona State University. So it's a discipline with rubrics and assignments and methodologies and all of that. And it's an ancient practice. For much of those 35 minutes, much of our 300,000 years as a species, we were asking nature for advice. We kind of forgot. We surrounded ourselves, especially getting a big city, surrounded ourselves with concrete and steel, and we've become disconnected, and it doesn't even occur to us that there might be some teachers that don't look like us. And still in many indigenous communities, it is still practiced, right? So it's an ancient practice and an ongoing practice in many indigenous places in the world. So really, there's a lot of solutions to the problems that we're facing today, courtesy of life, right? That if we can quiet our cleverness, not think we have all the answers, and be humble, then there's the opportunity to learn from that. And we can learn about nature's forms, right? The actual physical structures. How do they work? How do they serve? You're probably all familiar with Velcro. I mean, Velcro originally was inspired by a burdock seed. The little hooks on the end of a burdock seed is what created Velcro, so mimicking that form. We can also mimic process, so not just what shape it is, but how it's made, right? What about light? You know, the whole idea of chemical light, or how photosynthesis works, or how communication strategies work. These processes we can learn from, and we can learn from whole ecosystems. How are the ecosystem dynamics? Because cities are a big ecosystem, and how could cities learn from this? So when we do this work, we like to think of it as we've got our challenges over here, and we've got the world of biology and understanding nature on the other side. We got to figure out how to cross that bridge. And we got to figure out and build a bridge. So we start with the question of how might nature be? Just like I suggested in the beginning, we aren't the only ones that need to adhere to wet. You know, if I've got to build a glue that sticks underwater, I should ask the question, how might nature adhere underwater? So we call that the function bridge. We're walking across that function bridge with that question in mind. And when we play in the workshops this afternoon, we'll do that. We'll have those questions in mind. So then I think of it like the password. You need that password to cross the bridge. But then you're not taking the organism back with you. You're not taking the blue mussel, which is what we eat for dinner, which does glue underwater. We're not taking the blue mussel back over and farming it or harvesting it or extracting the glue out of the blue mussel. But we're trying to understand the chemistry of how that glue in the mussel works. How does that process work? And can we mimic that chemistry? And in fact, that has been done. So what might we learn if we actually stop to ask? Not ask the experts, not ask the scientists, not ask the research lab, not ask the companies, but ask the other organisms, the non or more than human. So I chose a bunch of examples because they come from here. They're stories that come from the rainforest, or at least from Costa Rica, that I thought might be inspiring for you. So, of course, you've seen geckos, right? Geckos can crawl in amazing ways. They stick to anything. It's like, how do they do that? And of course, this looks like, that's one close-up of a gecko's foot. But if you look even closer, there's all these little fine hairs. And each one of those hairs is attracted to the surface. It's called a van der Waals force. And when you add up all of those little hairs, kind of like static electricity, you add them all up, it's enough to help the gecko stick to the wall. But it's so, or the tree, or the leaf, didn't evolve to stick to walls, of course. It's so powerful that the gecko, that's why they peel their toes back. They have to peel their toes back so that they're breaking each one of those bonds at a time. Little tiny bonds, each one is small in force, but collectively very powerful. So people have been trying to mimic this, and University of Massachusetts has created one called Gexskin. I've got another one here that is a company called CTEX, and they've made, and it's a non-adhesive. There's no chemistry. It's just physics. It's just mechanics. And using nanotechnology, we have been able to print basically those little tiny hairs that are at the bottom of these geckos' feet. And their product's called nanotech. And you can imagine, if we're not gluing things together, then we can repair them when they break, we can disassemble them for recycling, we're not exposed to the toxins of glues. Like, it changes the whole equation just with a simple solution like this. Thank you, Gecko. You have some owls here. What do we know about owls? They're silent in their flight. And owls have a very unique feather, different than many, many other birds, most other birds, in that there's an extra layer, and you can kind of see it right here. There's like 3 levels of division. Of course, you have your main, and then you've got your secondary, and owls have a tertiary and often a 4th level of division that just really softens the edges. So you don't get that sound of water going over, or air going over the wings. So this company just put serrations, right, on the edges of fan blades. Their goal was to make a quieter fan, which they did, but it also improved the efficiency of the fan, right? So you get less mechanical noise, less energy going into moving air. Super simple, mimicking the form. Birds can continue to inspire. Of course, you have the 2 kind. I mean, you got to look at that and be like, how can you fly around with that huge thing in front of your head, right? And not be like falling forward all the time? Well, it turns out, if you've ever seen the inside or actually held one, they're very light. They're super, super light. But how can you be light when your job is to like smash open really hard seats? Right? You know, how does light and stiff work together? Well, it turns out that the design principle is it's basically a foam inside with a keratin sheath on the outside. Okay? And that keratin is like our fingernails. So that's stiff, but this is all hollow. It's a hollow matrix inside. And so you can get incredibly strong, but very lightweight. And so these have been mimicked. We can now use foaming agents, and we can create the skins, and we can mimic those properties. But it's not just big macroorganisms, right? We can also learn from the very tiny. Plenty of spiders here. As you've noticed, spider webs tend to stay intact and birds don't fly into them, right? We might accidentally walk into them in the forest, but birds don't fly into them. So some researchers were asking this question saying, man, like, birds fly into our windows all the time. In cities, you may not know this, but there's crews in the morning whose job is to go out and sweep up all of the birds that crashed into the windows every night. It's terrible. It's absolutely terrible. Millions of birds. And so they said, well, that's like reflective, and spider webs are reflective, so how come birds can figure that out? And what they did, when they looked closer at spider webs, they found that spiders intentionally spin, of course it's an evolutionary development, but in their webs, there are small fibers that reflect ultraviolet light. And birds can see ultraviolet light. We can't, but birds can. So it actually doesn't look transparent to a bird. It looks like clearly, like we would look at a fishing net or something. It would be a solid net, so easy for a bird to avoid that. So this German company said, brilliant, and embedded in glass little staple fibers that reflect ultraviolet light. And their windows have no bird strikes. Nobody hits those windows. Or no birds do. Well, 1 out of 1,000 do, but maybe that was just meant to be like a little natural selection. So you have but we can see through. For us, because we can't see ultraviolet light, we don't see those fibers, and it looks like a completely clear sheet of glass. Simple solution, no more dead birds. The product's called Ornalux. You can buy it today. You probably recognize that wing, right? The Morpho butterfly. And you may not know that there's no blue pigment in a Morpho butterfly. That is all structural color. And in fact, if you look at a Morpho butterfly's wing under a microscope, it looks like little Christmas trees. And each of the branches in the Christmas tree is exactly one blue wavelength of light apart from each other. So it's reflecting all of those light waves and bouncing them back up. So it's called structural color, and structural color is permanent. That's why you can buy the Morpho butterfly in the little case here in Costa Rica and bring it home, and 20 years later it's still that beautiful shimmering blue. That blue has not oxidized. It has, like our pigments, our genes, or whatever, they don't stay blue like that because we use a pigment instead of structural color. And so this company, Titian Fiber Corporation, has made a structural color fabric, made a dress out of it. There's a car that used that in their Nissan car, put it in their car seats. And of course right now it's a little bit more just like a fashion thing, but the industry of like dyeing our jeans blue is very, very toxic. It's hugely wasteful of water. If we can really master structural color, we don't use the toxins, we don't use the water, we don't throw things out because they've lost all of their color. Huge amounts of things that we can learn simply from just looking at the Morpho and a lot of other colors in nature. And a lot of organisms are structural color, especially blue. It's a very common one. There's a lot we can learn from butterflies. This is a swallowtail. This, just as this is brilliantly blue, this is called super black. This is like ultra, ultra black. It's blacker than any black pigment we can make. And of course, black has its purposes where it's super valuable, not just for looking fashionable in New York City, but you need things to stay black and not fade. Likewise, also structural color. This is a close-up of the wing. And here, the light is getting trapped in pockets. And that can be mimicked. So scientists have built materials that mimic that so you get ultra black. But we can also learn from the processes of butterflies, like how they see. Right? And they have, as we know, they can see colors that we don't see. And they have a much broader spectrum. These scientists developed a camera that sees like a butterfly sees, and they use special dyes to dye cancerous cells. And so during surgery, a surgeon can use this camera and differentiate between a healthy cell and a cancerous cell, and make sure that they're cutting out all of the cancerous cells by seeing like a butterfly. From the bees, as you might imagine, there's a ton that we can learn from the bees. This was actually a group of students in the Netherlands, or Belgium, excuse me. And they were inspired by how bees keep their hives cool. Basically, it's a combination of fanning with the wings and some dehydration off the legs. And they were addressing the problem of food waste in delivery in developing parts of the world, especially in Africa. Where you don't have refrigerated trucks. And so fresh food was going to waste because it wouldn't last. And so they developed these portable systems inspired by the bee that had like 2 weeks of the life of food. And of course, if we're not wasting food, we're not wasting the energy that went into producing that food, we're not wasting the water that went into producing the food, the time, the energy, the effort. Right? So it's just making us more effective at doing what we need to do by learning from the bees. But we can also think about how are bees so good at doing routes where they're pollinating and they're very efficient in optimizing their plan through a field of flowers. And they do so in such a way that ensures the energy they're getting out of those flowers corresponds to the energy they need to do the work, right? Get their pollen and so on. We can map that. So we can actually use algorithms. And this company called Routific has made bee-inspired algorithms to help small delivery companies that every day have a different route, just like a bee has a different route it needs to go through flowers, and do it in the most optimal way. So you save gas, therefore you save carbon dioxide emissions, you save time, you save money, because the bees helped you design your route for the day. Also can learn from ants, right? Talk about navigating traffic, right? Ants are the masters of navigating traffic. You can develop algorithms, and they've been done, on the rules of traffic engagement from ants and apply them to traffic zones. So this they tested in Guangzhou in China, and by playing with the traffic lights, they could control the traffic and were able to reduce idling times and therefore emissions by 18%. Right? And if you're not sitting there waiting for the light to change and you've got traffic moving, again, less fuel, less emissions, happier people, right? Waiting in traffic is more fun. They probably should do this in San Jose. Maybe my life will be easier again here. But we know that the ants aren't stuck in traffic jams. Right? So there's lessons there. Beetles, you have no shortage of beetles here. Beetles, of course, all have an exoskeleton, and as you know, when insects molt, they have that soft tissue, and then they have a sclerotization process, a hardening process that turns the soft tissue into what we know as that harder exoskeleton. A chemist by the name of John Warner was incredibly inspired by that process of hardening in the melatonin, refilling in the gaps, that he developed a new dye that isn't actually a hair dye in the sense of adding pigment, but it restores your original color. So this is going from gray to getting back your original color. No toxins, right? Being a hairdresser is one of the most toxic jobs you can have. And if you can, and it's not good for yourself either if you're coloring your hair gray, but this restores your natural color inspired by sclerotization of beetles. Okay? So there's brilliant minds that are connecting these things that we're trying to solve for with processes and forms and examples in nature. This was a group out of Brazil that was inspired by tank bromeliads, and not just the fact that they can store water, but they're little mini ecosystems, right? So you've got all the nutrient storage and so on. And they were addressing deforestation in Brazil and recognizing that a lot of the seedlings that were being planted weren't making it. So they designed this biodegradable protector, if you will, inspired by tank bromeliads. It opens up, it captures and stores water, it channels the nutrients, and the survivability of seedlings in the time before this biodegrades goes up like 100-fold, right? And so instead of 1 out of 10 making it, now 8 out of 10, right? Which is huge. We got a lot of deforestation to do. And they were inspired by these bromeliads, nuclearia is the name of that group. But even the smallest of smallest that we can't even see can inspire us. These are tardigrades, also known as water bears. You may have heard of them. They've been to the moon and back and lived to tell about it. So tardigrades can withstand complete desiccation. And they completely dry out. They go into a dormancy. They go to sleep for years at a time, and then they recover. And what makes that remarkable is if any of us were to dehydrate like that, what happens in our cells when the water disappears is the sugars in our cells turn to crystals. So they get pointy because they're crystals. And when they're pointy, they poke holes in the sides of our cells. And then when you add water back in, you have holes, and so now all the water leaks out. Right? That's why dehydration is so dangerous for us. What the tardigrade does is it has a special sugar in its cells that rather than turning into crystals, turns into like an amber. It's just smooth. So it goes into like an amber stasis, and then you add water, that dissolves, and there was no holes punctured in the side of the cell walls. So scientists got really excited about this and now use it as a preservative for vaccines. Because half of the vaccines don't make it into an arm. Because, especially in the developing world, because there's a break in what's called the cold chain. They can't stay refrigerated to stay preserved. So you either add a lot of chemicals, like mercury, which we did for years. We know it's not good to inject into little babies. Or you keep it refrigerated, which is very hard to do in most of the world, where vaccinations and vaccines are most needed. But if you put trehalose, a mimic of trehalose, into the vial, you don't have to keep it refrigerated. And it's completely dehydrated. It gets injected, the water of the body dissolves it, and there it is. You can use it to stage. You can get multiple shots because you can say how long before that dissolves and releases the next dose. They're also using it for DNA stabilization. So for research that needs to keep DNA stored, what have we done? We put it in a deep freeze, right? We put it in liquid nitrogen and try to keep it deep frozen. Huge energy expenditures for keeping DNA stable. Or you use trehalose and then you don't need any refrigeration. So then you don't need the energy. But even at the largest scale, we can look at how ecosystems work. Right? So we go to the micro to the macro, and we know nature is a beautiful example of a circular economy. Right? That's what we're trying to design right now, is a circular economy. This is a small example from a brewery near where I live in Montana. And one thing you notice is it doesn't look like a typical flow diagram for business, where it's bring in the product, make something, distribute it, and then there's an end line, right? It's a line, and there's trash at the end. Every one of these arrows goes in and goes to someplace else, right? That's what a circular economy looks like. And it's not this. It's not glass bottles, get used, recycled into glass bottles, get filled, get used. That's not a circular economy. Nature doesn't do that. Right? A bromeliad does not break down and turn into a bromeliad. Right? We know when a bromeliad breaks down, it goes into frog guts and worms and this and that, right? It gets distributed and then built up, and it's up and down. There's no upcycling and downcycling in nature. There's just cycling, right? It's just in flow. Right? Who's to say that an eagle is the upcycled version and the beetle is the downcycled version, right? I'm sure the beetle would disagree. So, thinking about how do we design our systems where we can close the loops, we can begin to learn from nature how that works. We're also working with companies that are saying, how can we function more like the forest next door? So I've been working with this company for 25 years as a carpet company, and we started with how to better design carpets, and now they've said, how can we better design our factories? And literally going into intact wild factories and saying, how much carbon is fixed? How much water is stored? How much biodiversity is here? What's the albedo? How is temperature managed? And then trying to make that same thing happen in the factory next door. And it's hard, but they're doing it. And not only are they getting the ecosystem service benefits of doing it, they get employee retention, they get happier and healthier employees, they increase productivity. I mean, it's just showing up on so many different places. We're doing the same thing with data centers. We're doing the same thing with car factories, like trying to find a way that we can act and function more like these systems. And that's just a very small slice of all the stories and examples. I tried to focus on one, as I said, where the inspiration came from what you should all be familiar with. So we can look at emulate, and all these examples are really important examples of learning, taking those lessons, applying them, and hopefully being better humans at the other end of the door. But we also believe there's two other really important essential elements to the practice of biomimicry. The second is reconnect. Right? You can't learn about or learn from nature unless you're in nature. Right? So you actually need to spend time. Seeing an elephant and learning from its flapping ears doesn't make any sense unless you see that elephant in context. Right? So reconnect is about remembering that we are nature. Right? We're not like hard, square, technological robots. We're biological beings. So that reconnect is reconnecting ourselves with nature and literally being out there and recognizing this large interplay, this dynamic system. It's a very important part. It's why we do our workshops in beautiful places like this, to help facilitate that process. And there needs to be an ethos. You can't learn from nature, even if you're learning in nature, and then design a better nuclear warhead. You can't learn how the lotus cleans its leaves and then use toxic chemistry to mimic that. So it's the whole package of having the right reasons for why we're learning from nature. It has to come from that deep place of respect and awe. Right? Being like, oh man, we are just toddlers. We are just toddlers. We don't know anything. Right? We actually have to go back to this stage, right, when we were so young, and we knew we didn't know. Mama, Papa, help me figure this out. And as toddlers, we were toddlers of this planet. But we act like teenagers, right? I know it all. I don't need you to tell us anything. We have to go back to this, this is the biomimic's posture. Right? That's how, if you see someone like that, there's a good chance they want to be or could be or are a biomimic. Right? But it's that childlike curiosity, awe, and wonder of nature that makes this possible. And when we do that, and this is why I do this work, it's why the folks that are here with me are doing this work, is we deeply believe that then we can create conditions conducive to life. All of them, not one species on this planet, but all 30, 40, 50, 100 million species. We can create those conditions. We can become welcome. We can become a welcome species here. Imagine all the species in the forest, they're all having their own little conference while we're in here, and they're like, do we want them to stay, or do we want them to go away? Right? We would like to want to be able to stay. Right? And so we have to act like good guests. And that's what this is about. It's about reconnecting, which I think is part of our humanity. Right? What it means to really be a generous, giving human. That, I think, we have the potential to do. So what do we do? Where do we start? Well, aren't you lucky? Because you get to do this a lot. Not everybody does, but this is what I tell everybody. That you start by going outside. Number one, go outside somewhere where life is thriving. Somewhere where more than humans are doing their thing. Even if it's getting on your knees in a sidewalk and looking at that sprout coming up through the sidewalk and seeing what life is doing. And then breathe, right? It's okay to take the studying hat. What's going on here? It's okay to take that hat off for a minute. You just breathe. You just be. You just be out there. And listen. Listen to what nature is trying to tell us and what it has to offer us. And then we can echo back. Then we can echo back what we're learning. And that's the work. And that's the work. Thank you. So I'm happy to answer any questions that might come up for people. What was the bat species? Did you recognize it?
That's Dermidura. There's two species very similar to that. This one from Norway, this one probably Dermidura lawsona.
I don't remember.
Chris helped me find that picture. I was looking here, and so Chris is a dear friend. We've known each other for 18 years, and he's an incredible naturalist from Costa Rica, and has been all over. You actually have probably seen some of his guidebooks and his illustrations. Now he's getting embarrassed. But so when I was pulling this together, I was holding up pictures. I was like, in Monteverde? No. Only the Oso Peninsula. Okay. You know, like I just pull it up so that I could hopefully get what you all have. Great. Yeah, Annabelle, and then up here.
Dayna, in your experience working with biomimicry, what relevance, what role does it play in interdisciplinary work for the function?
Yeah.
Is it something that needs to be a key piece?
Absolutely. All of biomimicry is interdisciplinary. In fact, we have a phrase that says, if you're doing biomimicry alone, you're not doing biomimicry. Okay? And so, actually, it'd be kind of fun, the folks that came with me, we've got Fiona coming from Australia, who's got a business background, right? And then we've got Lise coming from North Carolina, and she's got the environmental science background. And we've got Andrew in the back from Tennessee, and he's got a chemistry background. We've got Nick from Colorado, who's got a built environment and an engineering background. Chris is a naturalist. Edie's here as a systems thinker. Michelle in the back there, she's a lawyer, right? And so applying these in so many different ways, and in fact our master's degree has that level of diversity, right? Because it takes everybody figuring this out, and Rebecca, you've got an energy background. Rebecca's in the master's program. So there's this, just a huge diversity, that's super key, a really big part of that interdisciplinary. Yeah, thanks, that's a great question. Yeah?
Yeah, I would just like to know more how much interaction or do you have anybody, you talked about indigenous knowledge. Is there any, connections with indigenous groups? I work with an organization on Pine Ridge designing systems to help address, all the major issues there.
Yes.
And using indigenous knowledge and systems thinking and all these things.
Great.
So I'm just wondering.
Absolutely. Yeah, and it happens in various ways in different places. One of our students who worked for the Environmental Protection Agency in Montana and worked with the tribes was bringing biomimicry and bringing traditional ecological knowledge together to help solve some of those kinds of challenges. I'm sure Pine Ridge is the same. That say, and again, as I mentioned, in indigenous cultures, that asking nature, but they're sort of forgotten even there in some places. So reminding them that TK and indigenous ways of knowing are just as valid to solve these problems here. And so yes, in various capacities, in different ways that we're connecting. The group that we just had in the Osa Peninsula, we're going up to Vancouver Island next. We go to 6 different habitats with this group. And the place where we're staying is an indigenous group that is working on bringing traditional ecological knowledge back to conservation issues and bringing land stewardship in there. So yeah, there's a number of ways that that's happening. Thank you for that question. Yeah. But we've barely scratched the surface of this.
I was interested, you talking about the ethics of the procedure. What's that chemical that keeps the tardigrade blood from
The trehalose, the sugar.
trehalose?
Yeah, TREHALOSE.
And when I see things like this, what's the source
Absolutely.
for those? Where does it come from?
Yeah. Well, it doesn't come from the tardigrades. Can you imagine, like, China milk? Yeah, no. So yes, that has to be synthesized in the lab. And that synthesis process needs to be benign. So we also work with green chemists. And here's a good example, because I started with the blue mussel, and I told you they made a glue. And so they made a glue not extracting from the blue mussel. They actually used a soy protein. And I can't remember the exact, but basically it's a couple of functional groups that they noticed were part of the blue mussel's protein that created the adhesive properties underwater, allowed it to cure underwater. So using the soy protein, they added those functional groups to the soy protein. And where they were using it was in making plywood. This was Columbia Forest products, so making plywood and OSB and other sheet goods of gluing wood together. And the idea would be then plywood would be, wouldn't expand in the water. It wouldn't also off-gas. That was the beauty, so no toxic off-gassing. And it was very well acknowledged for its environmental benefits. And then people started looking, well, how are you actually making this glue? And they were using a kymine, kind of a nasty process that was producing some nasty byproducts. Even though the product was benign, the byproducts were not. And so when that was called out, then they had to go back and change their process so that part would clean up. So you're exactly right. The ethos, it's hard, right? We live in this larger system, and I flew here, right? I produced carbon dioxide in the plane. I didn't produce it, the plane did, but I'm here, right? So I have some of that burden. So it's hard, but the goal is to just try to keep bringing all the parts of the system together as deeply as we can in that ethos to ensure the making of the trehalose or whatever it is uses low energy processes, benign chemistry, causes no harm to humans or other life forms, right? Is socially responsible, environmentally responsible in that process. Yeah. Great question, thank you. Yeah.
Thanks for the talk, it was very interesting. I was just wondering if artificial intelligence is playing a role in biomimicry.
That's a great question. Artificial intelligence and biomimicry. biomimicry. So that's a hot topic for us now, trying to figure out what role that plays. What I can tell you, and this is important for everybody to know, that the artificial intelligence that you can now chat in, there's actually not intelligence involved at all, right? It's just natural language processing that it's learned how do we talk, just like, but what is biomimetic is just like that's how infants learn to talk, right? They're not using intelligence. They're just like, mom always says the noun, the subject before the verb, so I should say the subject before the verb. So that brain development process does mimic, right? So artificial intelligence in its own way has some mimicry. What we're trying to learn is how it can help create the tools. So I'm guessing many of you spend a lot of time in the primary literature or have written your own papers, all that stuff. That's hard to access, all of that information. It's hard to find, it's hard to build the connections. Like, how do you find that little bit, that little nuance that is the mechanism that we need to understand? Right now, it's all just human brains trying to figure that out. And so there's some work, so we have a database in the nonprofit side called asknature.org. And you can go there and say, how does nature create color? And you get a whole bunch of examples. All of that has been human curated. And the team that's working on that database is working with IBM's Watson, which is the artificial intelligence that IBM developed a while ago, Watson. And of course, it's continuing to develop. And to see if we can train Watson to go into the primary literature and find, like, basically that function bridge. Can Watson be the function bridge that walks over to the primary literature and finds the connections that need to be found? So it's still in its infancy, but there's some interesting potential. But I would add one important thing. It's not just an algorithm. It's not just a science. I always say in the graduate program that there's an art and science to biomimicry. Right? It's finding that and recognizing that there's some very unobvious but very interesting lessons that can be learned. And so I still think it's going to need a lot of humans looking at this. Yeah. Thank you.
Well, what we're all up against, of course, is climate change. We have a constraint there, time-wise. Very serious constraint. It looks like what you guys are doing is a major move in the right direction. Now, how do we get this through to all these major corporations and politicians that control the way our progress starts dealing with climate change?
Yeah.
I don't see it happening on the scale it needs to happen.
Yeah, that's a great question. I mean, that's the big question. Like, how do we make this happen fast enough and scale it fast enough? What I can say from the inside, from working and showing up in these corporations and from traveling, is there's more good news than we get to hear. For example, I was at the World Expo in Dubai. And of course, this is every country putting forth their best face. Every pavilion I walked into, from Pakistan to Zimbabwe to Japan, they had three things in their pavilion. Nature, and how we've got to take care of nature. Sustainability in its own right, and young innovators. What are the young of our country doing? Unfortunately, the U.S. was not one that had any of those three, but that's another story altogether. But I saw it over and over and over again. Poland's pavilion was called Inspired by Nature, right? At COP26, COP20, the last one, I get all the numbers, sadly, there's too many. The one in Glasgow, everybody was talking about nature-based solutions. Everybody was talking about bringing this to the table. Since the pandemic, our phone has been ringing often. You know, I mean, we were always a little bit ahead of our time, but now it's just like, you know, right now we're talking to Ford, talking and or working, I can't tell you because there's lawyers involved and confidential, but Ford, Microsoft, Google, Amazon, Danone, Procter Gamble, Unilever, and in the past also, and these that we've worked with Nike, we've worked with Shell Oil Corporation, like, I mean, it's widespread. And so it is starting to happen. And I think we're starting to reach that. Of course, we're reaching a number of curves. Some that we don't want to go that way, and others that are starting to go that way. What will happen in our lifetimes? It's hard to say, right? It's really hard to say. My work is about, like, let's kind of get out of the way, because we saw with COVID, right, when we got out of the way, how quickly life rebounded. And so that's where I hold some hope. You know, if we have these reservoirs, we have this incredible knowledge, we have these places where life can start clawing its way back, it will. It will. Or we go extinct. Also an option. That's not clear yet. Edie.
This is great data. I think I heard you first talk 15, 18 or so years ago, and I was so excited. And seeing this again, I have the same excitement from it. And one of the things I really love seeing is the business applications. Those of you who are working on the business, and I'm really interested in the scaling, like what percentage of glass windows now have the bird-friendly windows? And how do you, I guess, look to make sure the marketing scaling up? I'm sure you've thought about that quite a bit.
Oh yeah, all the time.
Because these are also brilliant, how to get them everywhere.
Yep, and there's, in fact, at ASU, we're running a grant right now we're calling Lab to Market, right? And how do you address those? What's interesting and sad at the same time, it has a lot to do with embodied energy. So it's just like we don't see an evolution like huge leapfrogs. Like it's not like we went straight from being amphibians to flying in the air, right? Like it took a lot of iterations because there's a lot of embodied energy just in that gene pool, right? And it's these incremental steps. Same of human innovation. So even though we have brilliant solutions, there's a lot of infrastructure. There's a lot of embodied energy. So, you know, Interface Carpets, working with them and designing new ways of manufacturing the carpets, all well and good, except 3 years ago they just sunk $10 million into this piece of equipment, right? And that's not what we're talking about here. Well, they have to cost run that full $10 million out. Or some of these innovative ones that are coming in, you know, how to be a market disruptor when everybody who's already in the market, no different than, hey, this is my niche, who are you coming in trying to take over my niche, are doing everything to push against that. So even though the solution's brilliant, and we can all be like, oh yeah, that needs to happen now, there's still a lot of, because systems reinforce they don't want to shift, right? They don't want to shift. And so that's part of the work too. And this is where I hold hope, right? Because it's all the story we tell ourselves. It's all the story we tell ourselves. For those of you who are in the United States, a few years ago, we discovered how bad trans fats were for us. You guys remember that? It was a big, like, oh my God, trans fats. Before that news came out, they were in 80% of food in the grocery store. 5 months later, it was 10% of food in the grocery store. Because we all said, nope, we don't want it. And the companies went, okay, nobody's buying this anymore, we've got to change it. So when we start telling ourselves a different story, that's the overriding factor, right? That's what flips us, when we tell a different story. You know, and it may take several more Cat 5 hurricanes before we're like, oh, maybe climate is changing. Right? We saw Mayor Bloomberg, right? When that superstorm Sandy hit New York City, he became suddenly like, oh yeah, climate change is real, I need to do things differently. So we may just need more of these strong signals, which we're going to get, whether we like it or not, and then that story starts changing much faster.
I have a question, maybe it's a good wrap up one, I don't know where we're at in time, but just to bring it back to, this institute does so much to support field work in Monteverde, which is also very famous for its diversity. There's so much we don't know about forum process and the system here. So I'm wondering if you have any recommendations for folks that are doing that field work to create more literature that helps the biomimics find information.
That's a great question. Yeah, great question. So there's kind of two things that I encourage for biologists and researchers. Is one, like, do all the work that you were doing, figure out those pieces, put them together. And when you can figure out something, what we call the strategy and the mechanism, when you talk about not just what, but how does it do it? You can say, well, yeah, the gecko climbs the wall. How? Tell us how. How does that work? Or this happened, you know, how? How does that happen? How does that signal happen? How does that process happen? How does the, what's it look like? And then, and I'm starting to see it in a lot of papers, like the last 3 sentences in the scientific paper are like, and the medical industry might be kind of interested in this idea, right? Or like just putting some of those key words around, this could maybe have an influence on electronics and electronic processing, or AI might be interested in these ants I'm studying. You know, whatever it might be, is just putting some of those keywords in helps. The other thing is, now that you've heard this, is just having some sensitivity and awareness where you can start matching what does it mean to be a human navigating this world, and what are the challenges with the work that you're researching, and see, are there things out here that I can also actually begin to understand more and make those connections, right? So it's, I was trained as a biologist, and we're trained to, like, you know, of course you're like, I must focus so I can publish, you know, I must have my little niche so I can publish. But like opening that up, and opening it up in scope, not just for the larger ecosystem, but what lessons here could I gift humanity? Okay? What could I gift humanity? And having that in mind, hopefully that can be part of what's required. Thanks for that question. Awesome. Great.